Hi, this is Miss Litton, and this is Chapter 16, How Populations Evolve. If you haven't listened to a presentation yet or learned, you want to review what is evolution and what is the evidence for evolution. Now we're going to talk about that process. So the first thing we're going to do, okay, when we talk about this process is we're going to focus on 5 things that can contribute to evolution. And we're going to learn this by the 5 fingers. And what I'm going to have you do is put your Chromebooks at half mast. And we're going to just watch this. Have your hand handy. It will help you when you learn as it's going through. And this will be somebody that you recognize.
The 5 fingers of evolution. A thorough understanding of biology requires a thorough understanding of the process of evolution. Most people are familiar with the process of natural selection. However, this is just one of 5 processes that can result in evolution. Before we discuss all 5 of these processes, we should define evolution. Evolution is simply change in the gene pool over time. But what is a gene pool? And for that matter, what is a gene? Before spending any more time on genetics, let us begin with a story. Imagine that a boat capsizes and 10 survivors swim to shore on a deserted island. They are never rescued and they form a new population that exists for thousands of years. Strangely enough, 5 of the survivors have red hair. Red hair is created when a person inherits 2 copies of the red gene from their parents. If you only have 1 copy of the gene, you won't have red hair. To make this easier, we will assume that the 5 non-redheads are not carriers of the gene. The initial frequency of the red hair gene is therefore 50%, or 10 of 20 to...
Okay, so I want to just jump in there. It really works with this analogy. What do you call genes? You call them a pair of genes, right? What pair are we referring to when you have 2 copies? I'm sorry, what? Homologous pairs. Homologous pairs. That's what they're talking about that, so keep that in your head.
Total genes. These genes are the gene pool. The 20 different genes are like cards in a deck that keep getting reshuffled with each new generation. Sex is simply a reshuffling of the genetic deck. The cards are reshuffled and passed to the next generation. The deck remains the same, 50% red. The genes are reshuffled and passed to the next generation. The gene pool remains the same, 50% red. Even though the population may grow in size over time, the frequency should stay at about 50%. If this frequency ever varies, then evolution has occurred. Evolution is simply change in the gene pool over time. Think about it in terms of the cards. If the frequency of the cards in the deck ever changes, evolution has occurred. There are 5 processes that can cause the frequency to change. To remember these processes, we will use the fingers on your hand, starting from the little finger and moving to the thumb. The little finger should remind you that the population can shrink. If the population shrinks, then chance can take over. For example, if only 4 individuals survive an epidemic, then their genes will represent the new gene pool. The next finger is the ring finger. This finger should remind you of mating because a ring represents a couple. If individuals choose a mate based on their appearance or location, the frequency may change. If red-headed individuals only mate with red-headed individuals, they could eventually form a new population. If no one ever mates with red-headed individuals, these genes could decrease. The next finger is the middle finger. The M in the middle finger should remind you of the M in the word mutation. If a new gene is added through mutation, it can affect the frequency. Imagine a gene mutation creates a new color of hair. This would obviously change the frequency in the gene pool. The pointer finger should remind you of movement. If new individuals flow into an area or immigrate, the frequency will change. If individuals flow out of an area or emigrate, then the frequency will change. In science, we refer to this movement as gene flow. All 4 of the processes represented by our fingers can cause evolution. Small population size, non-random mating, mutations, and gene flow. However, none of them lead to adaptation. Natural selection is the only process that creates organisms better adapted to their local environment. I use the thumb to remember this process. Nature votes thumbs up for adaptations that will do well in their environment and thumbs down to adaptations that will do poorly. The genes for individuals that are not adapted for their environment will gradually be replaced by those that are better adapted. Red hair is an example of one of these adaptations. Red hair is an advantage in the northern climates because the fair skin allowed ancestors to absorb more light and synthesize more vitamin D. Thumbs up. However, this was a disadvantage in the more southern climates where increased UV radiation led to cancer and decreased fertility. Thumbs down. Even the thumb itself is an adaptation formed through the process of natural selection. The evolution that we have described is referred to as microevolution because it refers to a small change. However, this form of evolution may eventually lead to macroevolution or speciation. Every organism on the planet shares ancestry with a single common ancestor. All living organisms on the planet are connected back in time through the process of evolution. Take a look at your own hand. It's an engineering masterpiece that was created by the 5 processes I just described over millions and millions of years. Can you recall the 5 main causes of evolution from memory? If you can't, hit rewind and watch that part again. But if you can, give yourself or your neighbor a big 5-fingered high five.
Okay, so now, what I want you to do is with your bio buddy, come up with the 5 things that contribute to evolution. Go. Okay, so what was the pinky finger? Small populations can lead to evolution. The reason why is they're more prone to being impacted by chance. So now I need you to think on both sides of the argument. This is going to prepare your brain for later information in this chapter. If a small population contributes to evolution, then what could stop evolution? A larger population, because it's not influenced by chance. Okay? What's this one? The ring finger. Non-random mating. Meaning your random mating would be, okay, whoever wants to have sex, yay. Okay? That's random mating. Non-random mating is saying, I choose you. I choose you. And when you choose a specific individual, then you're selecting. That's a sexual selection. You're selecting for certain traits to get passed on, right? So if non-random mating contributes to evolution, if you wanted to stop evolution, all mating would have to be what? Random. Just have everybody drink. Okay, what's the, that does contribute to random mating. What is the middle finger? Mutations. Okay, so mutations, where are my blue-eyed people? Raise your hand if you've got blue eyes. Okay, just Till and I, that's it? All right, well, Till. Okay, so in that situation, say Pete, in that situation, okay, blue eyes is a mutation. Okay, so you would have to stop mutations from occurring in order to prevent evolution. Do you see the counterpart to that? All right, and then what about the pointer finger? Gene flow. So these are alleles, new traits moving in, immigration, or out. That's going to affect. So how would you stop evolution from occurring then? No gene flow of any kind. And then what's the last one? Adaptations. And adaptations make you better suited to your environment. And that's natural selection we're talking about, right? So to stop evolution, there would have to be no selection, meaning of a population of flies, of a population of cheetahs, of a population of frogs, no one adaptation was better than another. Okay, do you think that that could ever be stopped? No, because organisms have variations, and some of those variations are better suited for that particular environment, and they are selected for. So in a nutshell, if you can't stop the 5 fingers, then what will always happen? Evolution. Now here's where the argument comes into play. Some people get upset about saying new species are created. Because who do they believe created those species? God. Only God. Again, I'm not belittling. Okay? But they're saying God created this species, and God specially created this species, and God created this species. I have to tell you, the species definition is not as firm as you would think it would be, and most biologists really don't care. Because when you have snakes, you could have snakes like in Florida, okay? And this population of snakes, okay, you look at them, you recognize them, they look like the similar group and they're interbreeding. But they will also have sex with their immediate neighbors. So are they a population? If they're still interbreeding with each other and making viable offspring, if their fitness is not hampered in any way, then you really can't call these two different species. Do you agree with that? And these guys will have sex with their neighbors, and these guys will have sex with their neighbors. But if you take species number 4 here in Middle America and try to get them to have sex with the ones in Florida, they won't. So they're definitely two different species, but where do you draw the line? See what I'm saying? So scientists don't go, oh, this is a species, so God made this and God, it's not like that. It's like, it's hard to draw the line always on saying this is a species. In fact, there's like 16 different definitions of what a species is. And we'll talk about that later when we talk about macroevolution. Now, I would like the oldest bio buddy to handle this page right here. Go ahead. Now, is this happening right now? Yes. Okay. So if a species is changing, if its traits are changing, if we're increasing antibiotic resistance, right, in bacteria, then what is occurring? Evolution. Evolution is occurring now. Within our lifetimes, we are seeing it. Okay, next bio buddy, you got an easy one. Explain what a population is. Okay, so that's what a population is called. Okay, so they're interbreeding in one area. Now we need to differentiate between the types of evolution. Other bio buddy, go. Okay, so when we talk about microevolution, we're talking about changes within our population. How many of you have been to Hearst Castle? Okay. Did any of you notice the size of the beds at Hearst Castle? Yes. They are very what? Yeah, they are short. If you go there, you're short. Okay? Hearst Castle was not built all that long ago. What does that tell you about our general population? It used to be what? Shorter. We have gotten taller. If you have a change within your species, we're all still Homo sapiens, that is referred to as microevolution. Okay? If you change to an entirely new species, that would be macroevolution. We're going to talk about macroevolution in chapter 17. Okay? But evolution, remember, is just change over time, any change over time. So I want to give you an example of microevolution. This is a yellow-bellied three-toed skink. Okay, yellow belly, three-toed like Yoda, okay, skink. You can see it has legs, pterodactylish, right, and feet. See them down here? Okay, now, this yellow-bellied three-toed skink, some of the species are starting not to lay their eggs, but keep them inside for longer amounts of time. The reason is climate change. And where they are living is getting colder, and as a result of that, then that was selected for. If you had a mutation where you kept the eggs in a little bit longer than one who laid eggs right away as soon as they were formed, you were more likely to survive and reproduce. Now, currently, those yellow-bellied three-toed skinks that keep their eggs inside are still currently mating with yellow-bellied three-toed skinks who lay eggs. But if it starts to become where they only mate with those that keep them inside, then what kind of evolution has occurred? Macro. Currently, what would it be referred to as? Microevolution. And I'm just showing you, this is the article that I got it from in order to talk about it. Okay? All right. Now, on your notes, the first thing I want to do is in 16.1. Okay, number 1. A temporary change, seasonal, or changes during an individual's lifetime is not evolution. It must be heritable. If it's heritable, what is it? It's in your genes. Good. Evolution is a change in traits governed by alleles in a population. A population is a group of single species living together in the same geographical area. Individuals do not evolve. Make sure you make that bold. Individuals do not evolve. Specifically, it's a change in allele frequencies in a population over time. The change in allele frequencies in a population over time. On types of evolution, microevolution is within a population. Macroevolution is large scale, forming what? New species. Perfect. Okay, now this is when you're going to want your digital piece of paper, your regular piece of paper, and your calculator. Okay, at home, same stuff. Okay, I'm going to hover on some slides for a few minutes. I want you to be dialed in because I will be able to teach you almost the entire chapter within the next few minutes. Okay, and I'm going to ask you to apply and think. Do not be distracted by anyone around you. Stay with me the whole time. Okay? All right. So let's take a look at this population. What do you think these are? What are they? Boars. Okay. Warthogs? Yeah, okay. Let's just call them boars because we got a letter B up there. All right? Now, these boars, how many are in this population of boars? How many? 7. There's 7 in this population. It's kind of a small population. Stay with me. Okay? Now, this is a diploid organism, so it has 2 copies, right, of every trait. Do you agree with that? Okay. Now, looking at each of these individuals, right, they either have big B or they have little b. All right. So I'm just going to make a chart right here. The big B allele versus the little b allele. Now, I have 7 individuals in this population, so how many total alleles do we have? 14. Okay? So now, with your bio buddy, figure out how many you have of each allele. Go ahead. You may think it's simple, but just do it. Once you counted the big B alleles, you shouldn't have to count the little b alleles, right? If you count the big B alleles, how many did you have? 7, right? So there's only 14 alleles out there, so the little b alleles also have to be 7, okay? What I'm doing is I'm saying if each of these boars took their 2 alleles that are on their homologous pairs, and all of them took them and throw them in the gene pool, right? I would predict what percentage of them would be the big B allele in this gene pool right here. Yes, 0.5 and 0.5. Do you agree with that? Okay, now, that's just saying everybody in their population throw their 2 alleles in, we're in the gene pool. We are going to now, when we talk about population genetics, we're not talking about 2 individuals having sex. We're saying if this population has sex. So our Punnett square has to reflect that. Because remember, individuals don't evolve. Who evolves? Populations. So now, here's my Punnett square. You can make a Punnett square too. Okay? Here's my Punnett square. In my Punnett square, I have big B, little b. Because what I'm doing is I'm looking at all the alleles and the frequency of alleles in my population and saying, if they are mating, what would I predict here? So what is the allele frequency of the big B allele? You just worked it out for me. 7 out of 14 is what? 0.5. Okay, and little b is what? 0.5. It has to be because you're either big B or little b, right? If we had worked out that the big B allele was 0.6, what would be the little b allele? Okay, good. All right, so this is 0.5 and 0.5. Do you agree with that?
Yes.
Okay, so now, if big B mated with big B, that would be big B, yes? And in this population, what's 0.5 times 0.5? 0.25. Big B, little b right here, also 0.25, right? You can finish this, finish it out. Is this what you got? Okay, now, so if you knew in the gene pool, because what emerges out of the gene pool, okay, is the population is going to emerge out of the gene pool, how much of that population would you predict to be homozygous recessive? 25%. So if there are 100 in your population, how many of them would be homozygous recessive? And if there were 1,000? 250, right? What portion of the population would you predict to be homozygous dominant? 25, right? And how about heterozygote? 50%. Do you see that? Okay. All you're doing is, on your Punnett squares now, you're putting the allele frequency out there and then predicting here what you would get in all of your zygotes. In all of your zygotes. Now let me tell you, you can start with this number right here and work your way back to these numbers. Or you can start with these numbers and work your way forward, right? Because if I told you 25% of the population expressed the recessive trait, you would know in order to express that recessive trait, you would have to be little b, right? Notice I couldn't work off the dominant trait. If I said, oh, 75% show the dominant trait, right? Those that show the dominant trait could be big B, or they could be what? Big B, little b. So you would always have to work off the recessive trait in order to figure back. Now, let's try doing it with the people here in this room. Currently in this room, okay, there are 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 2, 4, 6, 8, 29 individuals. Do you agree with that? Okay, there are 29 people in this room. How many of us have blue eyes? 2. Okay, 2 of us in this room have the recessive trait. Okay, how would we represent that recessive trait? Little b, b. Do you agree with that? What's another way to write little b, b? B squared. B squared, right? B times B. We just did 0.5 times 0.5, 25, right? B squared equals 2 over 29. Do you agree with that? The recessives in this room, there are 2 recessives of the 29 people in this room. So, take your calculator. What is 2 divided by 29? What is it? 0.06. Give me the next number. Okay, so let's just say 069. Are you okay with that? Such a small number here. Are you okay with that? Okay, you did that because you took the square root. So that means B is equal to 0.069. Are you okay? For just making it easier, can we say 0.07 just to make it easier? Are you all right with that? Oh, we didn't take the square root? Oh, sorry. Take the square root of 0.069. Sorry, I'm jumping ahead. Oh, I like that better. 0.26 what?
0.262.
Okay, so let's say 0.26. Okay, take your square root. Now we have solved for b, little b. What else could we solve for? How could we find out big B?
2 minus 29.
Not 2, not 2. I'm not gonna say, oh, 27 out of 29, right? Because that's gonna be big B, and what? Big B, little b. How can I solve for big B? 1 minus 0.26. Because if you're not little b, what are you? Big B, right? That's the only other thing you can be. Right? Remember back here when we were doing our Punnett square? If you weren't big B, what were you? Little b. Okay? So now, here we are. If we're not little b, we're big B. So what is 1 minus 0.26? 0.7 what? 4. Exactly. Now I know what's in our gene pool. I'm predicting what's in our gene pool in this population of period 3. The frequency of the big B allele is 0.74. The frequency of the little b allele is 0.26. What can I predict now? Of the 27 of you that have the big B anything trait, how many of you are big B, and how many of you are big B, little b? Let's go back to our Punnett square so you remember, right? Look back here. Let's redo our Punnett square, this time within this classroom, right? We have big B, big B, little b. What were our two numbers again? 0.26 and 0.74, right? Do you agree with that calculation? So now you need to do big B times big B, which is 0.74 times 0.74. What is that? 0.5 what? 0.55. Okay, now, how many people do we have in this room? 29. What is 0.55 times 29? Do the math. So, what is it? Tell me the number again. What's 0.55 times 29 people in the room? 15.9? 15.95. So we're going to say how many? I would predict 16 of you in the room are big B. Okay, how many did we say were little b? We counted us. How many? 2. So that means big B, little b, what's 16 plus 2? 18, right? And what is 29 minus 18? 11. So we would predict 11 of you are heterozygotes. Do the math to see if 11 of you are heterozygotes. That would be this number and this number, right? So that would be 0.74 times 0.26. What is that? And you have 2 of those, right? What's 0.74 times 0.26? 0. Point what? So we'll say 19, and you have 2 of those, right? 2 heterozygote boxes, big B, little b, right? So what is 2 times 0.19? 0.38. And how many people do we have in the room? 29. So take 29 times 0.38. 11.02. Just as we predicted. Right? So, what this is telling you, okay? Just step back for a minute. Let's talk about where we did this. We looked out in this classroom, and we know that we have brown-eyed, we're just simplifying it here. We have brown, black, right? We have brown-eyed people, and we have what? Blue-eyed people. We took the percentage of blue-eyed people in the room, and we know the only way you can be blue-eyed, right? The only way that you can be blue-eyed is if you were little b, right? So Another way of writing little b is writing what? B squared. So we knew 2 out of 29 was 0.069. We just took the percentage of the room of blue-eyed people. You just take the recessive trait percentage, get the square root to solve for b. Once you have little b, you know it's either little b or big B. So once you have little b, you know big B. Once you have those two values, you know what's in the gene pool. You can predict what will come out of that gene pool. You can predict each of those. Okay, so we could predict how many of you would be homozygous dominant, because we just took 0.74 times 0.74, big B, right? 0.74 times 0.74 times 29 people in the room. And that's how we figured how many of you are homozygous dominant. There's two ways to be a heterozygote. You can be big B, or little b, big B. So we just took the big B value times the little b value times 2. And then we just multiplied it by the number of people in the room, and we predicted how many of you were heterozygotes. Now, you're not always going to know exactly the letters when you're doing these Punnett squares. You're not always going to know maybe what the letter is used. So to simplify that, whenever you're talking about the dominant allele, they call that P. And whenever you're talking about the recessive allele, they call that Q. So this is P and this is Q. So this box right here, how could I write that in the most simplest way? I could say P squared. This box is P what? Q. This box is P Q. And this box is Q squared. So would you agree with me that I could write P squared plus 2PQ plus Q squared equals 1? What? Oh, sorry, I forgot the square. Thank you. Q squared equals 1. Would you agree with that? Yeah. All I did was write your Punnett square out in a linear equation, right? Because this is my homozygous dominants. What are these? Heterozygous, these two boxes, big B, little b's. And what's this? Homozygous recessive. This is how it plays out in the population. Where did this come from? This came from a gene pool. What were our two options in our gene pool? P plus what? Q equals 1. The P's in the pool, right? So take a look right here. Here are your two equations. P plus Q equals 1. P is the dominant allele frequency. Q is the recessive allele frequency. This right here is our allele frequency, our allele for how often does it come up. And then how that plays out in your population, that's this, the genotypic frequencies. The allele frequencies in our gene pool, you just look at all the different combinations you could have out of our gene pool. If our gene pool has got P's and Q's in it, then I could reach in my gene pool and I could pull out 2 P's, right? Or I could pull out a PQ or a QP. That's why we say 2PQ, right? I could reach in my gene pool and pull out 2 Q's. You can start right here, and this is what we did. How many blue-eyed people are in the room? And there were how many? And from that, we could solve for Q, right? We had 2 out of 29 that have blue eyes in this room. Using that, we solve for Q. Once you have Q, you can solve for P. Once you have P, you can predict the P squareds, and you can predict the 2PQs. Now, I needed to teach you this math to tell you this thing. Our allele frequency for Q in this classroom was 0.24. Is that accurate? 0.26. Okay, sorry. Was 0.26. If the allele frequency for little b, which is Q, right? If it changed from 0.26 to 0.3, then what would happen to P? It would be point. And if the allele frequency changes, what has occurred? What can cause these allele frequencies to change? Small populations due to chance. What else? Non-random mating, liking one combination of alleles over another. What else? Maybe P is mutating to Q or Q is mutating to P. What else? Gene flow. Maybe a whole bunch of blue-eyed people move in here. Or what? Maybe blue-eyed people do better on the test. You see what I'm saying? If the allele frequency changes, evolution is occurring. Since we can't stop these 5 things from happening, what do we know is happening? Evolution. If we're still interbreeding, then what kind of evolution is it? Microevolution. If it prevents us from breeding within our population anymore, it is macroevolution. That is the chapter. Okay? Tell your bio buddy, how you feeling about that? Okay? Now, let me give you some practice right here. Okay? Here is a practice. Look, you can write it down. You can work on it at home. In your notes, I gave you more practice problems. Okay? Here are flowers. I'm going to tell you the purple trait is recessive. You should be able to tell me how many of these flowers are homozygous dominant, how many are recessive. You should be able to do that. And that would be great practice for you. Okay? Write that down or take a picture. You have it in your PDF of this presentation. You have this. And then let me give you some notes. Okay? Go to your notes. Underneath microevolution and the peppered moth. Population genetics studies the diversity of populations at the level of the gene. Allele frequencies. A gene pool is all the alleles in the population. All the alleles in the population. And I explained that. You can read B, you can read C. D. Genotypes are as a result, so you get genotypes as a result of the allele frequencies. Genotypes as a result of the allele frequencies. I gave you PP or P squared is homozygous dominant. What is PQ? Heterozygotes. And then you have QQ or Q squared is homozygous recessive. 2E, if the allele frequencies for a particular trait remain unchanged, P and Q values remain the same, generation after generation, then that trait is not changing or evolving. Okay, then you have the rest of that box. Okay, I'll give you the rest of the notes later, other than skip to the next box in case you want to have some practice over the weekend. You see at the bottom of the next box on microevolution and Hardy-Weinberg equilibrium, do you see where I have a link there where it says practice problems? You can do some more practice problems there too. Okay, questions or concerns? No? Have a great weekend, or I'll see you mañana if you want to look over your test. Hope you're feeling better, Rain.